High above the Earth, orbiting silently in the vacuum of space, an extraordinary idea is becoming reality, beaming solar energy directly to the planet's surface. Long considered science fiction, this concept, known as space-based solar power, could one day provide clean, continuous electricity to anywhere on Earth. But how exactly would this work? Can we really send energy through the air across space safely and efficiently? And who's already building it? The core idea is deceptively simple. Instead of collecting solar energy on Earth, where clouds, atmosphere, and nightfall interfere, you collect it in space, where sunlight is constant. Giant solar panels mounted on orbital satellites capture energy 24/7. That energy is then converted into microwaves or laser beams and transmitted to Earth, where a special receiver called a rectenna converts it back into usable electricity. No wires, no fuel. Just focused power sent straight from orbit. The benefits are immense. Space-based power beaming offers a consistent, weather-free energy supply, perfect for off-grid regions, disaster zones, and even military operations. Unlike Earth-based solar farms, orbital power stations can generate electricity day and night. Some models estimate that a satellite the size of a football field could generate as much electricity as a small nuclear reactor, without the waste or risk. The concept has been around since at least the 1960s, but the technology wasn't ready. Now, with advancements in material science, satellite miniaturization, and precision beam control, countries are racing to make it happen. Japan has led multiple successful microwave transmission tests. The US military is developing a project called Spider to beam power from orbit to Earth-based receivers. And the European Space Agency has launched Solaris, a program exploring commercial-scale orbital power. The biggest technical hurdle is beam accuracy. To safely and efficiently transmit energy over thousands of kilometers, the system must keep a focused beam locked onto a moving receiver without interference or scattering. Microwave beams are low intensity and safe for humans, but misalignment or atmospheric distortion can result in significant energy loss. That's why engineers are designing automated alignment systems that use real-time feedback and orbital positioning to maintain exact focus. In simulations, precision control systems have demonstrated the ability to lock onto a target with less than a 1-meter margin of error, even from 36,000 kilometers away. These breakthroughs could allow working tests by the late 2020s. There are also political and environmental concerns. Who controls orbital energy infrastructure? Could it be used for surveillance or even weaponization? International law has not yet caught up to space-based utilities, and the first to deploy may set the standards. Still, the potential upside is enormous. A successful beam test in California recently showed that 1 kilowatt of power could be beamed over 90 meters with pinpoint accuracy. In Japan, researchers are planning tests over several kilometers. By 2030, we could see cross-continental beams connecting orbit to remote receivers, pushing boundaries not just technically, but politically. Imagine powering an entire city without touching a single local energy source. No pipelines, no generators, no solar panels. That's the vision driving this research. In disaster zones, temporary rectenna fields could be deployed to receive emergency electricity from space. In remote communities or military bases, energy could arrive silently and safely, even when roads are blocked or weather cuts off traditional supply lines. The flexibility alone changes the equation for global energy security. And with enough satellites, countries could reserve orbital energy for peak demand periods, like heat waves or grid failures, within the next 10 to 15 years. Some experimental designs go beyond solar. They propose harvesting energy from the Earth's magnetic field or collecting power from sunlight reflected off other orbital structures. Compared to ground-based solar or even fusion, space-based power beaming has a unique strength geographic independence. You can build it in orbit, beam it to the Arctic, a mountain village, or a ship at sea. And unlike traditional infrastructure, there's no need to lay cables or roads. With multiple satellites and beam paths, redundancy becomes easy to implement. It's scalable, secure, and once launched, requires no fuel to operate. Timelines vary. Some commercial demonstrations could happen before 2030, with limited power deliveries to specific government or industrial clients. Full-scale orbital grids are likely further off, possibly 2040 or beyond, but the pieces are falling into place. Launch costs are dropping, especially with reusable rockets. AI-driven targeting is improving beam lock precision. Microwave beam safety has already been proven in lab and field tests. NASA, JAXA and ESA have all projected pilot-scale tests by 2027 to 2029. If funding continues and international cooperation holds, large-scale deployment could begin in the 2030s, growing toward full orbital grids in the 2040s. As the technology matures, space-based energy may not just be about convenience, it may be essential. Earth's energy demands are rising fast. Space-based solar could allow us to meet those demands without building more fossil plants or risking energy wars over limited resources. And as the geopolitical map shifts, whoever controls space power may control energy security for entire regions. It's a quiet race already underway. Beam-powered cities, off-grid independence, and clean energy from space are no longer just fantasy. They're forming on drawing boards and test sites around the world. Will your country be first to receive power from orbit, or will others seize the sky? In 15 years, this could be as routine as satellite internet. One thing is clear: the future of energy is about to rise above the clouds. Picture this. It's the year 2040. A global constellation of power satellites beams electricity to continents below. Energy arrives on demand, beamed silently from the sky to remote villages, coastal cities, military outposts, and floating offshore factories. Some satellites serve as international utilities, selling power across borders. Others are nation-owned, securing energy independence in an uncertain world. Rectenna fields have become common infrastructure, unobtrusive arrays of mesh and receivers tuned to the sky. With fusion still in development and fossil fuels declining, orbital solar has become the backbone of a new global energy network. It started as science fiction, but the orbit grid is here, and it's only growing. If you enjoyed this glimpse into the future, don't forget to like, subscribe, and share this video for more updates on space-based solar power.